Welcome all to my presentation. I am Shayak Mukherjee, a postdoc at PNNL, and I will present my research on scalable reinforcement learning control for distributed energy resources. As we are moving toward interconnected infrastructure systems, the complexity and dimensionality of the system is increasing, such as power grids. Therefore, the accurate dynamic model of the system may not always be known to the designer. With recent advances in sensing and data-driven techniques, we look forward to developing measurement-based controls. We can consider two approaches, such as approach 1 and approach 2, where in approach 1, we first perform a system identification and then perform the control. And in approach 2, we perform direct control. So here we shown in a two schematics. So in the first figure, we show that we can perform a system identification, and then we can design optimal controls using classical control techniques. However, what if the operating conditions keep on changing, and we also are adding lots of new renewable resources in the grids? So instead of running the identification multiple times, we can use reinforcement learning to compute the feedback gains directly. Therefore, the RL can be a viable solution which combines the optimality and adaptiveness. RL work in this way, where the controller, also known as the agent, tries to interact with the environment via the feedback and also receives reward signals. And it tries to optimize its actions in order to accumulate higher rewards over a particular time horizon. Now, with high penetration of inverter interface renewable resources, the dynamic performance of the grid are decreasing due to lack of inertia. Therefore, the operators need to design stabilizing controllers. However, designing controllers in a wide area fashion may suffer in tractability. Therefore, we look into bringing modularity and plug-and-play capability in this kind of designs. Along with the modular structure, we also propose to perform reinforcement learning in order to develop model-free designs. We use the terminal bus voltages of all these renewable resources to formulate this reinforcement learning algorithm. And localized learning also helps us to reduce the exploration time and the control dimension. We employ a linear quadratic regulator-based control design, which tries to minimize the energy of the states and the DERs, and that in turn influences other power system states to improve dynamic performance. We use the DER state measurements Y, shown here, and also the terminal bus voltage measurements V to formulate a fully data-driven algorithm to compute these controllers. The algorithm first gathers a sufficient amount of data, which are combination of DER states, exploration inputs U, and the terminal bus voltages. And thereafter, it solves for the optimal controller by solving an least square equation in an iterative way. And once we get computed the controller, we implemented this controller in a decentralized fashion on all the distributed energy resources. We show an example with simulations on IEEE 68 bus system where we implemented two wind farms. And each wind farm contains multiple wind turbine units, each with 1.76 megawatt. We first show that we increase in the wind penetration, the dynamic performance of the grid is degrading. Thereafter, we start to perform this kind of reinforcement learning designs. So we perform this three figure shows exploration phase of the grid where we added small perturbations at the active power inputs of the wind farm. Thereafter, we gathered this kind of data, and then we perform these control iterations to get converged solutions. And once we get the converged solution, we implemented the control back in the system, and we test with multiple severe faults, and we can see that the grid performance has been improved, and shown in this blue color with respect to the nominal performance, which is shown in the red color. We also experiment with multiple cases where we change the wind farm location, and we can also see that the wind farm location also plays some role in order to get sufficient performance improvement. And that is because of the amount of coupling it has with the grid states. So in conclusion, we have developed a fully model-free approach and also a decentralized design, which helps to implement or bring in scalability in the feedback control designs. The proposed methodology also enjoys faster learning and reduction in feedback gain dimensionality. So future research will be directed toward more distributed RL designs along with providing sufficient performance guarantees. Thank you.